Okay, so let's start. Türk oldu değil mi? So we have seen first order equations. Actually, we have seen only linear ones and separable ones. And the other type of ordinary differential equation which we will encounter most are the second order ordinary differential equations with constant coefficients. Actually, if the coefficients are not constant, even if they are linear, they are not in general easy to solve, although we know that there are solutions and so on, but finding solutions might be a problem. However, in case of constant coefficients, we have the whole theory. So a constant coefficient second order linear differential equation is something like this, right? Şöyle yazayım. Ya da hepsini x koyalım. Tamam, şöyle. Equals, let's say 0. So here, y function of x is the unknown function. And a, b, c are just constants. Okay. How can we solve this? Well, we have so-called characteristic equation. And what is that? Well, you look for solutions of the form e to the power mx. M is a real number, but we will see that actually sometimes it's real, sometimes it is complex. So we look for exponential solutions to this equation, and there is a good reason why we should expect such solutions to exist, because you see I have derivatives, and when you take derivatives of this e to the power mx, you just get basically the same thing multiplied with m, right? If you take derivative once, you get mx m times, sorry, e to the power mx. If you take second derivative, you get m squared and so on. And when you plug it here, you will get a quadratic equation in m, and then you can just solve it and see for which m values you have a solution. So you just take its derivatives, sorry, m squared e to the power mx, and then plug them into the equation to get what we will get. We will get a times second derivative. Second derivative is just m squared mx, right? So m squared e to the power mx, and then b times m times e to the power mx plus c times e to the power mx equals 0. And you see that e to the power mx is a common term, and it is never 0, right? E to the power mx is never 0. Therefore, I can just divide the whole equation by e to the power mx, and we get am squared plus bm plus c, and this is called this is so-called the characteristic equation. Actually, if you write this equation as a linear system of equations, you get a 2 by 2 system, and then you have a matrix, and this equation becomes the characteristic equation of that matrix. So this is the name came from actually linear algebra. You may also think it that way. So you just solve this equation and find the solutions for m. So let m1, m2 be the roots of the characteristic equation. Then the solution can be written as follows. We have 3 cases. Case 1, so this m1 and m2, so the roots of the characteristic equation, are both real and they are different. So m1, m2 are both real and they are different. In that case, the solution given like this: e to the power a constant. Since this is a second order equation, solving this equation involves 2 integration, because you have 2 derivatives. To get rid of the derivatives, you have to integrate twice, and each integration gives you 1 arbitrary constant, integration constant. And since you integrate twice, you should expect 2 arbitrary constants. And indeed, the solution becomes just this: c1 times e to the power m1x plus c2 times e to the power m2x. Okay, so this becomes the solution. C1, C2 are just real numbers. Case 2, they are real and they are equal. So the 2 roots coincide. Okay. Of course, this is not something happens always. It's a very rare case, but it happens. In that case, these 2 solutions are the same. M1 and M2 are the same. Therefore, you have to come up with another solution. And this is what we do: T1 times e to the power M1x plus T2 times. In this case, you just put extra x term here, and this becomes the general solution. So C1, C2 are C1 and C2. And this actually corresponds to the case where the matrix formulation of this equation is not diagonal but has a Jordan form. Okay, so you have 2 eigenvalues, but they are the same, and the matrix you obtain is not diagonalizable. It has a Jordan form, and then this is just the solution obtained from that matrix. So that is case 2. And case 3 is we have two complex solutions. M1 and M2 are not real numbers, so they are complex but not real. Okay. Of course, since the equation, quadratic equation, you know, we know how to solve it. So in this case, M1 and M2 are just nedir? Eksi B, değil mi? Artı eksi B kare eksi 4AC bölü 2A. So this means this B squared minus 4AC is negative, right? So that the roots are imaginary. Let's write these roots like this. Lambda plus minus I times mu, okay? Here lambda and mu are real numbers, and we know that mu is not zero, right? Mu is not zero, because if it were zero, then the roots would be the real numbers, but we know that they are not real. In this case, the solution becomes what? In this case, solution becomes C1 times e to the power lambda x cosine mu x plus C2 times e to the power lambda x sine mu x. Okay. Again, C1 and C2 are just real numbers. So that's the general solution. Okay. Bir tane örnek yapalım. Şöyle. Okay, let me write this way. Initial value problem. What's an initial value problem? Initial value problem is a differential equation, but we know that a differential equation has infinitely many solutions. We just pick up one solution by asking that solution to satisfy certain conditions. We call those conditions initial values. For example, let's say our equation is this: y double prime, y prime plus y equals 0, and our initial conditions are y at, let's say, 0 is 1, and y prime 0 is, let's say, minus 1. So this means what? We have a second order equation, and we know that the general solution of this has two arbitrary constants, and I have two initial conditions which determines these two arbitrary constants. You may think of this equation as the equation of a physical problem. For example, let's say I have an object moving in a one-dimensional axis, and y is the position of the object. So y, let's say x, and or let's say yt. T is representing the time, and yt is this distance. Okay, is this distance from the origin. So this is the distance, this is the speed, this is the acceleration of the object. And we are given this equation which relates position, velocity, and acceleration. What is this? This is the initial position of the object, and this is the initial velocity of the object. Okay. So it's going in the negative direction with speed 1 unit at time 0. Okay. And I would like to know how the object moves in time. So how do we solve this solution? We write down the characteristic equation. What is the characteristic equation? You see, if it is a times y double prime, b times y prime, and c times y, the characteristic equation is just, where was it? So it is basically the same equation where the derivatives of y are replaced by the powers of m. So I don't have to go through the, bunu söyledim ama göstermedim. Right, if you have this equation, then the characteristic equation is just this, and it is obtained from the equation by replacing derivatives of y with the powers of m. Okay. So here, characteristic equation will be just m squared plus m plus 1 equals 0. So m is just, or 1, 2 is just minus 1 plus minus b squared, which is 1 minus 4ac, which is 4 divided by 2. So it is just minus 1 over 2 plus minus root 3I over 2, right? So this is our lambda, and mu is just this. Therefore, solution, which is just C1 times e to the power lambda t cosine mu t plus C2 e to the power lambda t sine mu t. Therefore, it is just e to the power minus t over 2 times C1 cosine mu is just root 3 over 2 t plus C2 sine root 3 over 2t. Okay, so that's the solution, general solution. C1 and C2 are just arbitrary constants. And then we can just find those constants. So let me rewrite the equation, the solution here, e to the power minus t over 2. And okay, C1 times cosine root 3 over 2t plus C2 sine root 3 over 2t. What were the initial conditions? Y0 was 1, right? So when I plug 0 here, I should get 1. So when I plug 0, I just get 1 here. T1 times 0, just 1 plus T2 times 0, and that is 1. Therefore, we see that C1 is just 1. Okay. What about the second condition? Well, first let's find the derivative. The derivative is just minus 1 over 2 e to the power minus t over 2, C1 cosine root 3 over 2t, C2 sine root 3 over 2t. Plus e to the power minus t over 2. And then derivative of this is just minus root 3 over 2 C1 sine root 3 over 2t plus root 3 over 2 C2 cosine root 3 over 2t. All right. Now, the second condition was this. Okay, so when you plug 0 here, you get 1 here, 0 here. Dolayısıyla buradan eksi 1 bölü 2 C1 minus 1 over 2 C1. Buradan da 3 bölü 2 C2 equals minus 1. C1 was already 1, right? This is just 1. So root 3 over 2 C2 is just minus 1. Burası eksi 1 bölü 2. Buraya geldi. Artı 1 bölü 2. Dolayısıyla burası yine eksi 1 bölü 2. So C2 is just minus 1 over root 3. Okay. O zaman ne oldu? Çözüm. So y is e to the power minus t over 2. C1 is just 1. So cosine root 3 over 2t minus 1 over root 3 sine root 3 over 2t. Okay. So that's the solution. Okay, unique solution. Ee, 254'ü veya 219'u almadıysanız hani bunlar sizde şu anda çok şey gelebilir. Çünkü normalde hani bu 1,5 aylık ders hani hepsini yapsak teorisiyle şunu yapabilirsiniz. İşte bir yerden ders notları vesaire bulabilirsiniz. Onlara bakabilirsiniz. Benim sayfamda 254'ü 2 sene önce vermiştim yazın. Onun ders notları var. Artı videolar da var. Ee, Onlara bakabilirsiniz. Ama hani bu ikinci sınıf differential equation'ı bilmeniz gerekiyor PD için. Tamam mı? Vardır. Peki şimdi burada bir existence uniqueness şeyleri de var da onları pas geçeyim. Şimdi evet. şöyle diyeyim. Şu integral curve kısmını anlatayım. So this is lecture 3. Okay, so uh, a surface in R3 is usually represented as the solution set of an equation. Something like this, x, y, z, and f of x, y, z equals 0. For example, if you let f, x, y, z, let's say example, it's a -1, then s is just x, y, z in R3 such that fx, yz equals 0, but that is just x squared plus y squared plus z squared equals 1, right? This is equal to 0 means x squared plus y squared plus z squared is equal to 1. So this is just the unit sphere, right? If this f is differentiable, then the gradient of f, namely, so defined by şöyle, ne kastediyoruz bundan? İşte f'in x'e göre türevi, y'ye göre türevi ve z'ye göre türevi. Is a vector field Yani bu şöyle bir şey olur. Şu diyelim ki f'in sıfır olduğu surface, yani f equals zero. Bu gradient of f her noktada x, y, z. If you take a point here, then gradient of f at that point is a vector which is perpendicular to the surface. This is easy to see. Why is that? If you choose any path, let's say going through this point, okay, so gamma t is a path on the surface. Well, since it is the case, f of gamma t is always, since it is on the surface, right? This is the set of points where f is zero. Therefore, so I am sorry, this is big F, not little. So this f of gamma t is zero, right? But I can consider this as a function of t, right? Gamma t is a function of t. It is this curve. And when you plug it inside f, you get a function of t. But this function is constant and equals zero. Since it is constant, its derivative will be also constant and equal to zero, right? So when I take its derivative of this gadget, f of gamma t, it should be still zero. But what is this derivative? So if I write, let's say, gamma t as in coordinates. So this gamma is a curve in R3. It has x coordinate, y coordinate, and z coordinate. So f of gamma t is then what? Şöyle yazayım. So we have this f of x of t, y of t, z of t equals zero, and this is true for all t, right? When you take derivative of this with respect to t, of course you get zero, but what is this derivative? Well, we apply, of course, chain rule. Derivative of this function with respect to t. So it is nothing but derivative of this function with respect to the first variable, which is del f del x, and then the derivative of the first variable with respect to t, which is dx over dt, plus derivative of the function with respect to the second variable, and then dy dt, and similarly del f del z dz dt. This is zero. Note that I can write it this way. So this is nothing but del f del x del f del y del f del z dot product with dx dt. I can write it as x prime, right? Dx dt, x prime, y prime, z prime, t. And this product is zero, right? So in the surface, I have this, my gamma, and its tangent vector, gamma prime t. is just since gamma is xt, yt, zt, its derivative is just x prime t, y prime t, z prime t. So the tangent vector to this curve is just this vector, and uh, this vector times this vector, the gradient of f, has inner product equal to 0. So this gradient vector, whatever it is, okay. Şöyle bir şey herhalde, gradient vector, right? So it should be 90 degrees, like this. Değil mi? Bu ne gösteriyor? So gradient vector is perpendicular to gamma prime. This is the tangent vector. Therefore, we have this. Şimdi biraz terminoloji var. Onları öğrenelim. Definition. Level surface. So if we have a function, so f is the function, let's say, from some domain into R, with differentiable function. This domain is, let's say, open subset. Okay, a set of the form SC XYZ in the domain such that fxyz equals c, where c is any real number, is called a level surface. Okay. Level surface of f. Yani ne demek bu? F'in C'ye eşit olduğu noktaların kümesi. Tamam mı? Aynı şekilde level curve de tarif edebilirsiniz, değil mi? Level curve nedir? F iki değişkenli bir fonksiyon olsun. Bunun işte şimdi S'yi surface için kullanıyor. Curve, level curve CC olsun. C epsilon diyeyim. Yani ne kastediyorum bundan? C epsilondan xy in omega such that fxy equals epsilon. So I have a function and I am looking at the values, no, the points in the domain omega such that this is just equal to epsilon. For example, let's say omega is just R2 the whole plane. Fxy is just, let's say, x squared plus y squared. Then what's the level curve? So this thing is equal to epsilon, right? X squared plus y squared is equal to epsilon. So this is just a circle. So our level curves are just circles, okay? So C epsilon. This is just x squared plus y squared equals epsilon. Belki şöyle mi yazmak? Neyse, evet. Yani yarıçapı karekök epsilon olan curve'ler. Level curve bu. Level surface da bunun 3 boyutlu hali. Ordinary differential equation'larda hani e, fonksiyon çözüm işte y olsun, x'in fonksiyonu ve onun hani grafiği bir tane eğri oluyor. PD'lerde işte en az 2 tane değişken olacak. Independent değişken, bir de dependent değişken, yani z, x, y'nin fonksiyonu olacak. Dolayısıyla çözümlerde işte x ve y'nin fonksiyonu olan nesneler olacak. Yani z, x, y diye. Dolayısıyla onların grafikleri de bu sefer surface'lar olacak. O yüzden hani bunları yapıyoruz. Şimdi ne kadar zamanım var? 3 dakika. Neyse kalsın o zaman. Bir dahaki ders implicit function teoremi hatırlatırım. Ondan sonra devam ederiz.